Let's jump right into this explainer. Our goal today? Uncovering the exact taphonomic, or, fossil-forming recipe that miraculously preserved the soft tissue weird wonders of the Cambrian period. If you've ever found yourself wondering how on earth the squishy, fragile biology from 500 million years ago managed to survive the ravages of deep time, well, you're absolutely in the right place.
So here's our taphonomic playbook for today. We're going to meet the weird wonders, decode the carbonaceous film, go through a step-by-step preservation guide, rank the fossil deposits, uncover the Cambrian chemical trigger, and finally look at the closing of the taphonomic window.
Starting off with Section 1, Meeting the Weird Wonders and the Paradox of Soft Tissue Preservation.
We're tracing the path from life on the Cambrian seafloor all the way to lithification, right? And here's the central paradox of that whole journey for geology students. Soft, squishy tissues simply shouldn't survive in the rock record. Seriously, scavengers and microbial decay usually destroy them in a flash. Yet the breathtaking biology of the Cambrian was captured in stunning detail. Just look at the fearsome 3-foot-long predator anomalocarids with its massive grasping claws. We've got the carnivorous Sydnea inexpectans, the famous lace crab Morella splendens, and even the super delicate sponge Diagonalus sciatiniformis with its entire skeletal network perfectly outlined. It's wild. How did this level of microscopic detail survive?
Which brings us to Section 2, Decoding the carbonaceous film and identifying the true taphonomic mechanism.
Now, the fossilization process that conserved these ancient creatures definitely isn't what you'd expect from a standard paleontology textbook. Most soft tissue preservation involves mineral replication, right? Like phosphatization, where minerals completely replace a gut, or pyridization, where early microbes are replaced by iron sulfides. But true Burgess shale-type preservation, it's remarkably different. It's the conservation of primary organic tissues as ultra-thin, two-dimensional carbonaceous films. The original organic material of the animal was quite literally compressed and conserved rather than just being swapped out for a totally different mineral.
Actually, we have to clear up a major red herring right here. Some researchers found these aluminosilicate clay minerals mapping perfectly onto the fossils and thought, this is the original preserving agent. But no, those clay coatings are actually a metamorphic byproduct. They formed millions of years later under immense heat and pressure, a process called green schist faces metamorphism. So they are absolutely not the original chemical condition that prevented early decay. That early preservation was strictly the carbonaceous compression.
Moving to Section 3, our step-by-step preservation guide on halting microbial decay. So, what's the exact trifecta of environmental conditions required to halt microbial decay before it destroys those primary carbonaceous films? Well, as a geology student, here is your direct, step-by-step playbook. To preserve a soft-bodied Cambrian creature as a carbonaceous ghost, you need 3 very specific things to happen fast. First, rapid burial in fine-grained, exclusively clay-rich sediments. Second, an environment with extremely low oxygen and low marine sulfate concentrations. And third, the ultimate secret weapon, an early carbonate sealing of the seafloor.
How does this actually look in a physical environment? Imagine a deep-sea burial setting. The key here is transportation. Living communities of these organisms were swept downslope by sudden storm events or density currents, crossing what we call the chemocline. That's the sharp boundary separating oxygenated water up top from the anoxic, oxygen-starved water below. This rapid burial in deep-sea mudstones under those anoxic conditions severely inhibited microbial sulfate reduction. And that's crucial because that reduction is the primary way organic matter rots and decays in the ocean. And then the final step acts like a giant geological vacuum seal. Bright bands of early diagenetic carbonate cements precipitated directly from the seawater right into the mud at the seafloor immediately after the animals were buried. This completely trapped the fossils. It physically restricted oxidants from diffusing down into the sediment, locking those fragile tissues safely away from microbes. That's what left behind those incredibly beautiful carbonaceous films instead of, a decomposed mess.
On to Section 4, Ranking the Fossil Deposits, and exploring why some sites are just undeniably superior.
By mapping out a 3-tiered classification, we can see exactly why some deposits globally give us a much more complete and pristine record than others. Tier 1 gold standards, like the Burgess Shale in Canada and the Chengjiang in China, sat at the base of remarkably steep underwater slopes. This basically maximized the physical energy needed to transport whole, live assemblages rapidly across the chemocline into those deep anoxic depths. Conversely, you have Tier 2 and Tier 3 deposits, like the Latham or margin formations, which sat in inner detrital environments. These flatter areas were either supply limited, meaning the currents just weren't strong enough to carry many fossils downslope, or they were decay limited, meaning the water remained entirely too oxygenated, letting decay run rampant.
And this is exactly why we've got to be careful when comparing the high-fidelity carbonaceous films of the true Burgess Shale with other well-known sites like the Emmy Bay Shale. Look, while Emmy Bay undeniably has incredible fossils, the taphonomic mode there is actually ambiguous and has been heavily altered by different weathering and mineral-based fossilization processes. Because of that, it is explicitly excluded from true Burgess-style preservation, which specifically demands that unique, unweathered carbonaceous compression.
Section 5. The Cambrian Chemical Trigger. A true global phenomenon.
So you might be wondering, why was this unique carbonaceous preservation so incredibly widespread across early Cambrian mudstones worldwide, but relatively unheard of today? The answer lies in a massive geological event known as the Great Unconformity. During this time, a massive expanse of reactive basement rocks was exposed to atmospheric weathering. This washed an unprecedented influx of continental weathering ions, things like calcium, straight into the early oceans. This massive influx highly alkalized the world's oceans, creating the exact chemical trigger needed to enable that crucial widespread seafloor carbonate cementing process we talked about earlier.
This global geological event directly impacted microscopic fossilization. Basically, this unprecedented period of continental chemical weathering created a temporary taphonomic window. The highly anomalous seawater chemistry allowed soft-bodied animals all over the planet to be immortalized as carbonaceous ghosts, totally defying the standard decay-heavy fossilization modes that dominate the rest of Earth's history. It was a real game-changer.
Finally, Section 6, Closing the Taphonomic Window. The End of an Era.
So why is this perfect recipe for carbonaceous preservation so incredibly rare in post-Cambrian rock layers? Well, as time marched on into the late Cambrian and Ordovician, the oceans changed. Vast carbonate platforms expanded, and they physically displaced those unique, fine-grained mudstone environments where the fossils were originally buried. Furthermore, global oxygen levels began to rise, and with it, bioturbation exploded. That simply means burrowing animals evolved and began churning up the seafloor. This constant churning disturbed those early burial environments, introduced oxygen, and permanently slammed shut the taphonomic window, ending those pristine, vacuum-sealed conditions required for Burgess-style preservation forever.
I want to leave you with a provocative final thought today, challenging you to imagine an alternate Earth. If the Cambrians' unique chemical taphonomy and low oxygen depths had never faded away, if burrowing animals hadn't evolved to churn up the ocean floor, would our entire understanding of evolutionary biology be completely rewritten by an endless, pristine record of soft-bodied carbonaceous ghosts? It's a fascinating concept to ponder. Thank you for joining me on this explainer, and keep questioning the ground beneath your feet.